In our next section, we're going to look at virtual device contexts, or VDCs, on the Nexus 7Ks, which are a way to do virtualization from the layer 1 point of view of the physical chassis. Now, we'll see the overall idea with the virtual device context, or the VDC, is that we're trying to split up a physical chassis into multiple logical units. And what this is going to do for us is going to provide us separation of the management plane in terms of how do we access the command line interface, or how do we access the APIs of the box, like from the REST API, how the control plane is going to be separated in terms of our layer 2 spanning tree instances, our layer 3 routing instances, and then also the data plane for forwarding traffic from a layer 2 Ethernet point of view, and then from a layer 3 routing point of view. Now, a key point being here is that virtual device contexts are specific to the Nexus 7000s and the 7700s. They're not implemented on the other platforms. The 9Ks, 6K, 5K, 2K, etc. Those only have one overall context that is going to be global to the system. Where Nexus 7K, we can split it into multiple logical units with the separate VDCs. Now, we'll also see that the Nexus 7Ks have multiple levels of virtualization. So we can do virtualization with virtual LANs, like we would see in our typical enterprise Ethernet switching environment, where we're trying to separate the Ethernet layer 2 data plane, meaning when we go to forward a traffic in one virtual LAN versus another one, we're not going to be able to send traffic between them unless we go through a layer 3 routed device. And it also means that we're separating the layer 2 control plane. So whenever a frame is received in by the switch, it's going to normally look at the layer 2 destination MAC address. It's going to correlate that with the separate MAC address table. And then this MAC address table is going to be built based on how our loop prevention technique, like spanning tree, is going to be either forwarding ports or it's going to be blocking ports to determine whether we can do MAC address learning or not. But key point here is that we're virtualizing both the forwarding engine, which is going to be the data plane, and the control plane, which is going to be the CPU calculation of the topology on a per virtual LAN instance. Same is going to be true with storage networking. We'll see once we get into SAN switching, we have a virtual SAN or a vSAN. From a logical point of view, very similar to a VLAN. This is going to be used to virtualize the fiber channel environment, or the fiber channel over Ethernet environment, where just like a VLAN, we're virtualizing both the data plane and the control plane. Control plane in the case of fiber channel is going to be the FSPF process, basically the routing process, or the fiber channel shortest path first process, and then also the data plane, which is going to be the actual routing of the traffic, or the switching of the traffic. Okay, also in NXOS, we'll see that we can do virtualization at layer 3 with virtual and routing forwarding instances, or VRFs. Same type of implementation as you would see in other boxes like regular iOS, iOS XR, iOS XE, Catalyst iOS, where we have different layer 3 routing tables, both for IP version 4 and for IP version 6. When a packet comes in, we look at not only what is the destination, but we look at a specific routing table or a forwarding table in order to make our routing decision or forwarding decision based on that individual instance. So we're going to have separation of the data plane based on where the packet is being received in. We're not going to have routing between the VRFs by default, so you can think of this as kind of like a VPN where the traffic is separated. And then we also have separation of the control plane. So if I have multiple OSPF routing instances or multiple BGP routing instances, those are going to be separated based on the VRFs. And OSPF process 1 for VRF 1 is not going to be able to talk to OSPF process 2 for VRF 2. So any of these three variations, VLANs, vSANs, or the VRFs, these are going to be logical virtualizations based on the layer 2 or the layer 3 topologies. Now, the VDCs are essentially taking this one step further, and within an individual virtual device context, we can have our own grouping of VLANs, vSANs, and VRFs, separating the management plane of how do we configure OSPF, how do we configure our management 0 IP addresses, how do we configure our user database, the control plane in terms of what are the VLANs that we're using, meaning that VLAN 10 in VRF 1, or excuse me, VLAN 10 in VDC 1 is not the same as VLAN 10 in VDC2 from a control plane point of view. So like from a spanning tree instance point of view, it's not going to be overlapping between the separate contexts. We're going to have multiple instances of spanning tree, multiple instances of routing working behind the scenes. Then likewise, same is going to be true from the data plane. When a packet enters the physical port, we're going to look at what particular virtual device context that port is allocated to, and it's only going to make its forwarding decision based on that individual VDC. So when we want to send traffic between contexts, we're going to have to do this from physical port point of view. And what I mean by this is that if we were to have a physical Nexus 7K that we have, let's say we have port number 1 and we have port number 5, and the first port is in VDC A, and the 5th port is in VDC B, and we want to exchange traffic between the two of these, we would have to take a physical cable, either a twin-ax or a fiber cable, and physically plug it in between the two ports of the same line card. So it's not the same as a virtual routing and forwarding instance where we can leak the traffic between the VRFs, or like a VLAN where you could do some sort of layer 2 tunneling between them in order to leak the traffic. In the case of a VDC, you have to physically exit the chassis, physically exit the line card, and then come back in if you want to move the packets between the different contexts. So from a logical point of view, you can think of these as almost separate switches, but they're separate switches that are contained inside one physical chassis. But from a management point of view, when you telnet or you SSH into the virtual device context, you don't necessarily know that the NXOS instance is virtualized. When you look at show run, show interface status, show IP route, etc., looks like it's going to be its complete separate isolated switch. Now, in terms of the use case for this, the main reason that you would typically use a VDC is that you want one physical chassis to be managing multiple roles in the network at the same time, so multiple logical roles. So you could be using, let's say, a Nexus 7718 that has 16 potential line cards, so lots of port density, where you may want to use this for your layer 2 Ethernet aggregation, and maybe you want to also use it for your core layer 3 routing, and you don't want that to be managed by the same team of admins. Okay, maybe you have a WAN admin team that's in charge of the routing topology, and you have a LAN admin team that's in charge of your Ethernet switching. You could put them in two different contexts, and then you would have separate user databases, separate management in order to access the box. Now, we'll also see that there's certain software features and certain hardware features that are going to require the usage of the virtual device context. For example, in the case of overlay transport virtualization, there's going to be a hardware limitation that you cannot do routing of a VLAN and also bridging of it over OTV at the same time. And then the same is going to be true of features like Fabric Path or VXLAN Leaf versus VXLAN Spine. You cannot combine all of these together within the same virtual context. And you cannot combine all of the different types of line cards or basically the modules of the Nexus 7K inside the same context at the same time. Okay, and we'll look at some of what are the specific limitations of that. Okay, another reason why you might want to do this is for multi-tenancy of the box. So let's say you want to do infrastructure as a service, or in other words, you're leasing the switch to a customer, and from their point of view, they think it's a physical switch that they are logging into and managing themselves. But behind the scenes, we have a larger chassis, and we have this split into multiple contexts. So we could have multiple customers that think they have their own separate physical switches, and from their point of view, the configurations are independent of each other. They're not impacting each other. But from our point of view, from a physical layer 1 point of view, we're cutting down on the number of, the amount of space in the data center, the amount of power, the amount of cooling, because we're virtualizing this into one physical chassis. Okay, so from the customer point of view, they're going to manage their own policies, like they log into the CLI and make those changes. But from behind the scenes, it's shared in one physical box. Okay, so physical resources are split between the multiple tenants or the multiple customers, but we're cutting down on the amount of physical footprint that we're needing in the data center. Okay, and like I mentioned, one of the other reasons why we would need to do this potentially is the limitation of some of the features. So OTV is one that we're going to look at. Some limitations are where you can or cannot run the feature. Another one is going to be the combination of the modules. So if we're running the Generation 2 modules, either the F cards or the M cards, there's some limits as to how you can combine them together in the chassis. And then also if we're running fiber channel over Ethernet, storage, networking, or SAN switching is going to require its own context. So this is a key portion of the overall physical design of the Nexus 7K. So if you are implementing this in production, or maybe you have an older chassis with older cards and you want to upgrade it to newer cards, upgrade it to newer code versions, you do need to be aware that not all of these modules and not all of the OS versions are supported at the same time in the same context. So this particular document here, the module comparison matrix, it goes over what is the, and you should, from the PDF, you should be able to link to this, but let me just search for this particular document, which is, if you just search for Nexus 7000 module comparison, which is this one, I/O module comparison matrix. What this shows you here is what is the specific part number. Okay, so for example, on the chassis that we're going to be using for our examples here, the card we have is F348XP, okay, which is going to be this one here. So it says what's the minimum release of code is version 6.2. Okay, this is going to be for the 7000 chassis. So ones that start with the part number N7K, this is for the 7000. Ones that start with N77, that's going to be for the 7700. You can see some of the cards like the new M3 module for the 7700. This needs the current latest release of code, which is 7.3. So some of these cards as well don't support the newer versions. Like the Generation 1 cards, if we scroll over to the left here, the way that you read this naming convention is the generation of the card. So for example, here we have M148 GS-11. This here, this first number is the generation of the card. So these are generation 1. The two numbers at the end are what is the supervisor that is required to run the card. And the last number is the number of fabric modules that you need in order to offer the card its full line rate. So for example, if we look at the card that we are using, which is the F348, it's F348 XP25. F3 means that it is Gen 3. XP25 means that you need supervisor 2. And 5 means that you need 5 by fabric 2 modules. Okay, which if you compare this to the 7700, there's less requirements for this. Like the fabric modules, they're using 3 of them because the 7700 has more forwarding capacity to the backplane than the 7000 does. Now, the second row down here, this one is the compatibility between which line cards can run inside the same VDC or not. So basically they're saying that if you were to have, let's say, M132XP, you can run this inside of a context that has other M1 cards, other F1 cards, or other M2 cards, or you could run in a context with M1, M2, and F2E. Okay, reason why is the F2 expanded version, or the enhanced version, this is not compatible with the first generation F card. Whereas the newer modules, you'll see like the M or the F3 and the M3, these are only compatible with each other. So if you want to run F3 on the 7700, you can run that with F3 and F2E or F3 and M3, but you cannot run it with the regular F2 or the M2 or the M1 and so on and so forth. So it's not necessary that you memorize this information. Just be aware that this is a platform limitation, that you cannot mix all of the modules together within the same virtual contexts. You can mix them together within the same physical chassis, but then when you go to split it up into multiple logical switches, there's going to be this potential interoperability issue that you would have to deal with. So you can see this inside the release notes for the individual software version, or you can see it in this particular document, which is, again, the module comparison matrix. Now, the number of contexts we'll see on the 7K that is supported depends on the CPU, it depends on the supervisor, where the first-gen supervisor allowed you to have one admin context for managing the box, and then 4 contexts for forwarding user traffic, or what we call the user VDCs. Where with the SOUP2 and the SOUP2 Enhanced, the SOUP2E, it supports 1 context for admin management, and then up to 8 contexts for forwarding traffic in the data plane. And in our particular case, we're using SOUP2E, so we'll see we have a dedicated context for managing, like for telnetting or SSHing to the box, and then other user contexts for actually forwarding packets in the data plane. Okay, so the admin VDC, you can think of this as kind of logically equivalent to the admin context of an ASA firewall. So this is used to control anything that is chassis-wide. So this is where you would be creating other contexts or deleting contexts, where you're assigning what physical ports are going to be used in a context, what resources are going to be allowed in the context, or what resources are going to be limited in the context, and then for remotely managing the chassis. So if you want to upgrade the code, for example, you would need to SSH in or telnet in or console into the admin context, and then the admin context is going to be in charge of all of these sub-user contexts. So for example, some of the more specific things that you can do only inside the admin VDC or inside the default VDC would be to create the other contexts, but a bunch of other things that relate to the chassis overall, like upgrading the code, if you want to install a new feature, if you want to change the quality of service system-wide, that's going to be one change in the admin VDC or the default VDC that is then going to affect all of the sub-user contexts. Now, you'll see that within the scope of our rack rentals, if you're using the Nexus 7Ks that we have, the admin VDC is going to be pre-created for you, and it's going to have any of the, or excuse me, both the admin VDC and the user VDCs are pre-created, and any of the features that you need in the user VDC, they're already going to be enabled for you in admin. So the steps that I'm going to go through here from creating the context and then doing the port allocation, you're not going to need to do that within the scope of the rack rentals, simply because if you have access to admin, or if everybody has access to admin, everyone could be overwriting each other's changes or basically deleting each other's contexts. So in a real production design, this is typically something that you just do once, and then from there on out, you're going to manage the box from the individual user context. That's where the data plane changes are going to be made. Like, what VLANs do I have? What is my routing protocol? Am I running Fabric Path versus VXLAN, etc.? That's not going to be done in admin. That's going to be done under the individual user contexts.